Hello, good morning. I don't even know what happened. It's already been final examination coming. This semester passed too fast. I just think it's just the beginning. And even this year passed so fast. I just got this curly hair. Other thing I didn't get. Well, I think I need to go back to my studies. I still left a lot of things. For example, the quiz. I hate those Indian professors. Very stupid. Speak nothing and it's not helping at all. Fucks that. Yesterday I checked the EOI or what. I think the score for pale for the capital is getting down. I remember it's that 15 points for a capital to apply for, but nowadays I think it's 10. So if it's 10, then I become a single person. I will be also like at 10. What for? Let's see. I gotta start, huh? Yosh. Finally, it's not going everywhere. Maybe get a little even longer, like this, maybe. So it will be looking good. And so I don't need to arrange it as always. Nowadays, it's still like this part. It's going everywhere. It's going like this. Very ugly. Okay, that's fine. Okay. No waste time. I have to go back to my studies. Go back to my studies. This colon is very stupid. I don't understand what it's talking about.
When we do the Einstein theory test, and the key point is that there's no volume change. Because we conduct the sample as fully saturated. And under the Einstein test for fully saturated sample, and the water is incompressible, there's no volume change. And this is our starting point to look at the point. So let's start the sample preparation isotopically consolidated to this point. And then we find the initial void ratio. And then we start loading. So this is the total.
这他妈的网课真他妈傻逼，我什么都看不见 there, here, this, that.
By following these no volume change rules, we know that we can start failure from the PV space because we know there's no volume change. So from the PV space, we have a horizontal line that is no volume change. And then we reach the failure point. Then we can project back this point to the PQ space. So we put a solid line here. This is exactly what happens. And we put a dotted line here. We said this might be the effective stress part we have. And we can see at the failure point, the total deviated stress and the effective deviated stress should be exactly the same. So this is total deviated stress, and this is total effective deviated stress. And the difference between the total mean stress and the effective mean stress, that give us the positive pole pressure. So that means for a loose sample above the critical state line, under the during the loading, the soil along the shear plane will generate a positive pole pressure because the soil is trying to contract, and the positive pole pressure to push the soil particles back to where it is to keep the volume no change. When we have a dense sample with less body ratio here or less specific volume, we do the unfringed shear test and we do the no volume change to reach the critical state. Then we project back this critical point back to.
操你妈！你钻你妈逼呢！你钻。
So we know the initial point, we know the final point. This could be the possible effective stress we have. And the difference at the failure point, the same Q level, the difference between the total stress and this is the total mean stress, and this is the effective mean stress, and the difference is the forward pressure. So for a dense sample, the solute trying to dilate and the volume has no change, then this suction water to keep the particles stay where it is, and there's no volume change. So this is in another way we can illustrate that for a dense sample, under-shearing will generate negative forward pressure, and for loose sample it will generate positive forward pressure. We have demonstrated this under the direct shear test as well. When you read the different books, sometimes you have the loose sample or the solute under the loose state, which is above the critical state line. They also called the sample as wet of the critical, and on the other side, under the dense state, they called it dry of critical. So that's the different names for the sample is staying above the critical state line or below the critical state line. So what is the basis of critical state solid mechanics in general? These are the key points when we look at
啥鸡巴玩意？我操！Afraid is similar to 嗯哼，你好，嗯。Of V. The volume of the increase. I think they mean the constant gradient. Drain test。操你妈！老子查查他妈老子的他妈文件，还鸡巴办不下来！我日你妈的！请允许我污言秽语。真他妈操！这么久，他连你他妈你手写你他妈应该写完了，1个月印不出来一个这，我你妈的逼的！操你妈！妈，中美竞争，中美赢定，中国赢定了！我操，就这效率。你4月20号才交由印刷厂，我他妈3月17号申请， 你他妈4月20号交到印刷厂，你他妈4月20号，现在5月10号了，你他妈还印不好，我操你妈的，我真傻逼，我操！妈老子无语了 ，TPS，TPS equals ESP, TSP equals ESP on PQ space. And dream test, the operator should choose total stress path. Total stress path. 啥他妈 total stress path? And dream means no volume change can occur. So VP path is horizontal line from the initial state to the CSA. So H VP path. VP path. 你这是 VP path 吗？ Horizontal from the initial state to the critical line. 什么鸡巴东西呀！我操！
So what is the basis of critical state solid mechanics in general? These are the key points when we look at the stress path and failure point. So under the dream test, the total stress path and the effective stress path, they always the same on the PQ state. And we can start to look at the failure point from the PQ state as well. When we do the dream test, we control the total stress path. However, the key point here is that we can start from the PV state to look at the no-volume change conditions. We can find the failure point. Then we project the failure point back to the PQ state. So for dream test, you start from the PQ state, and for the dream test, you start from the PV state to find the failure point, but the total stress path is what we can control.
What?
Now let's look at on the different spaces, the PQ space and the VP space, what are the normal consolidation lines and the critical C lines? We already know that on the semi-logarithm scale space, the critical C line and the normal consolidation line, they are parallel to each other. However, for the normal consolidation line, we also have isotopic consolidation line, which is this one here on the x-axis, or the one-dimensional consolidation line. The one-dimensional consolidation line is like the one we talk about in the compression test, when the soil is not allowed to move horizontally, only moving in the vertical direction. So that's one-dimensional consolidation. So in one-dimensional consolidation, because the vertical stress and the horizontal stress are not the same, it will generate initial dilated stress. So we can see here, these three lines in the semi-logarithm scale will have exactly the same slope lambda, but with a different starting point, which is the n, n0, and gamma. And these initial values here, they are the specific volume at a low stress, which means the log P is 0 and the P is 1 kPa. So that's a starting point here. So this is the relative locations between the normal consolidation lines and critical straight lines. And we're going to look at this to consolidate the soil along the different consolidation lines and then load the soil to failure. Let's look at the unjoined shear strength of normally consolidated clay. The key point here is the undrained test will have no volume change when the soil sample is fully saturated and no drainage allowed. And so this is the starting point we need to find out the undrained shear strength of this soil. We know that these are the equations to calculate the volume, specific volume, when the soil is under certain pressure. And also, we know that under the normal consolidation line, we can calculate the under the initial mean effective stress, which is P naught here. We can calculate from starting point to this consolidation point, what is the initial volume. And at the failure, when they reach the critical state line, at the failure, this point, failure point is on the critical state line. So on the critical state line, we have the final specific volume, and the mean effective stress will become a failure mean effective stress. And then we also need to use the mean effective stress on the critical state line on the PQ space to find the deviated stress at failure, because it is on this critical state line, so use the initial M. Once we find the failure at deviated stress, we can calculate the unjoined shear strength with a half of the QF. So now let's look at what is how do we get this one here. Let's look at the unjoined shear strength of normally consolidated clay. The key point here is the undrained test will have no volume change when the soil sample is fully saturated and no drainage allowed. And so this is the starting point we need to find out the undrained shear strength of this soil. We know that these are the equations to calculate the volume, specific volume, when the soil is under certain pressure. And also, we know that under the normal consolidation line, we can calculate the under the initial mean effective stress, which is P naught here. We can calculate from starting point to this consolidation point, what is the initial volume. And at the failure, when they reach the critical state line, at the failure, this point, failure point is on the critical state line. So on the critical state line, we have the final specific volume, and the mean effective stress will become a failure mean effective stress. And then we also need to use the mean effective stress on the critical state line on the PQ space to find the deviated stress at failure, because it is on this critical state line, to use the initial M. Once we find the failure at deviated stress, we can calculate the unjoined shear strength with a half of the QF. So now let's look at what is how do we get this one here. We know that when the soil is under a stress, with vertical stress and the horizontal stress, and the vertical stress is larger than the horizontal stress, we can draw more circles. When there's no shear stress acting on the x-plane and the y-plane, and the difference between sigma v and sigma h is the diameter of the circle. We also know that under the undrained shear condition, the failure point is only related to the initial force ratio or the initial volume. When they reach the failure point, we can find the effective stress path, the possible effective stress path from the initial point to the failure point. It seems that it has nothing to do with the total stress path. And total stress path is what we can control in the factual test. This means that when you control the sample, load the sample at different total stress path, the failure or the undrained shear strain will be the same. So what does it mean that when we have a different total stress path at the failure, the excess port pressure generated during shearing is going to be different. The failure effective stress will be the same, but the generated excess port pressure will be different. Sometimes when you have a total stress path like this, at the failure, it will generate a large positive excess port pressure. And the excess port pressure will act on the solid sample in the horizontal direction and the vertical direction the same. When you have a large excess port pressure, the most circle will move to the left. This means that even though the excess port pressure generated, the vertical and horizontal effective stress will be changed, will be reduced. But because they're reduced at the same magnitude, this most circle is still the same. If you generate a larger excess port pressure, and the most circle will move further to the left. And this is the peak shear stress we have on all most circles, and they are the undrained shear strength of this solo. And we also know that by definition, the deviated stress at failure is the difference between vertical stress and horizontal stress. And this is the diameter of the circle. So therefore, the undrained shear strength is the radius of the circle, and the QF is diameter of the circle. That's why we have the undrained shear strength is a half of the deviated stress at failure. We know that when the soil is under a stress with vertical stress and the horizontal stress, and the vertical stress is larger than the horizontal stress, we can draw more circles. When there's no shear stress acting on the x-plane and the y-plane, and the difference between sigma v and sigma h is the diameter of the circle. We also know that under the undrained shear condition, the failure point is only related to the initial voltage or the initial volume. When they reach the failure point, we can find the effective stress path, the possible effective stress path from the initial point to the failure point. It seems that it has nothing to do with the total stress path. And total stress path is what we can control in the factual test. This means that when you control the sample, load the sample at different total stress path, the failure or the unjoined shear strength will be the same. So what does it mean that when we have a different total stress path at the failure, the excess hold pressure generated during shearing is going to be different. The failure effective stress will be the same, but the generated excess hold pressure will be different. Sometimes when you have a total stress path like this, at the failure you generate a large positive excess hold pressure. And the excess hold pressure will act on the solid sample in the horizontal direction and the vertical direction the same. When you have a large excess hold pressure, the most circle will move to the left. This means that even though the excess hold pressure generated, the vertical and horizontal effective stress will be changed, will be reduced. But because they're reduced at the same magnitude, this most circle is still the same. If you generate a larger excess hold pressure, and the most circle will move further to the left. And then there's a peak shear stress we have on all most circles, and they are the unjoined shear strength of this solo. And we also know that by definition, the deviated stress at failure is the difference between vertical stress and horizontal stress. And this is the diameter of the circle. So therefore, the unjoined shear strength is the radius of the circle, and QF is diameter of the circle. That's why we have the unjoined shear strength is a half of the deviated stress at failure. So what is the unjoined shear strength of anomalies of consolidated clay? We start the derivation with this condition here. The initial volume and the failure volume are the same. And the formula we get is in this form here. The unjoined shear strength is a function of m, which is the slope of critical straight line on PQ space, and P naught is the initial mean effective stress, and the gamma, m, and lambda, they are the characteristics of critical straight line and normal consolidation line on this semi-logarithm space of the PD. So these are the steps to obtain the unjoined shear strength formula. Starting from this point here, the final or the failure volume, specific volume, is come from this formula here, and the initial specific volume is coming from this formula here. So let these two equal to each other, and then we get all the parameters and the initial and the failure mean effective stress in this formula. So the aim is to calculate, to find out this failure mean effective stress. Then we need to reorganize this equation to move n to the left-hand side, to move lambda logarithm pf to the right-hand side. Then we get this one here. And then we move this lambda to the left-hand side, and on the right-hand side, we get this logarithm of pf over p naught. To get rid of this logarithm, we need to put the exponential function on the left-hand side, and the right-hand side becomes pf over p naught. Now we can calculate the failure mean effective stress. And on this critical straight line in the PQ space, once we know the PF, we can calculate the QF. So the QF is the slope times the PF. And we also know that untreated shear strength is a half the QF and also is half of an PF. And if we substitute the PF into this formula here, then we get this formula. So this is how we get from the starting point to the end point to find the formula to calculate the untrained shear strength of the normal consolidated curve.
妈的，什么东西呀！我操！骨子里累累。SU equals
This is an example question to calculate the untrained shear strength of the clay. Also, we want you to calculate the excess hold pressure generated during shearing. For the first part,
尴尬。
very straightforward because we know all the different parameters here.
Straightforward 个屁！我操！ find and dream share strings. Oh, this could be great. And dream share strings. 不是他妈45度吗？操！
This is an example question to calculate the Andrew shear strength of the clay. Also, we want you to calculate the excess hold pressure generated during shearing. For the first part, should be very straightforward because we know all the different parameters here, and we can calculate the Andrew shear strength straight away. We just need to substitute the n, the p naught, the gamma, n, and the lambda into this formula, and we calculated Andrew shear strength of this non-reconsolidated clay is 26.59 kilopascal. For the second question is to find the excess hold pressure. So what we need to know is that at failure, what is the mean effective stress at failure? And at failure, what is the mean total stress at failure? Then we can calculate the difference between the mean total stress and the mean effective stress, and we can get the excess hold pressure generated. For the QF, once we calculate the SU here, we can find the QF, which 2 times of the SU. And once we know the QF, we can calculate the PF because using this slope M here. So you can see here straight away we can find the mean effective stress at failure. For the mean total stress at failure, we need to look at the QF point on this total stress path. The total stress path is starting from the P naught here, and then with the slope to get this PF, the mean total stress. So this is how we calculate the QF, 2 times the SU, and the PF is QF divided by M. For the total mean stress, it's starting from the P naught here. And then we start loading. We control the total stress. So at failure, we know the QF, and then the increment on the PF on this total stress path is 1/3 of the QF. So basically we want to find this point.
妈啥鸡巴意思？我操！总的。
And this total mean stress and the effective mean stress, this one here, the difference is the excess hold pressure generated during shearing, and it is a positive hold pressure because this is the non-reconsolidated clay, the OCR equals 1, the solid will behave like a loose solid.
什么鸡巴 QF、PF？ 我操他妈的！
So what about the over-consolidated clay under the undrained shear test? What is the undrained shear strength? This one is a little bit more complex than the normally consolidated clay. In this one here, we need to consolidate the solid under the isotopic normal consolidation line to reach the P max. And then we unload the solid to the current stress state. If it's isotopically consolidated, the unloading is still on this horizontal axis with zero deviated stress. And on this deviated stress, we have the normal consolidation line and the unloading line. And on this semi-logarithmic scale, we have a straight line coming down and a straight line going back. And the slope on the normal consolidation line is lambda, and the unloading line is kappa. It's similar to the sigma V and V space when we draw the normal consolidation line and unloading reloading line. But in here we use the logarithm P over the specific volume V. When we look at the initial, this is the initial state, and we have the initial volume. The initial volume will go through this normal consolidation line here, which is from here to the maximum mean effective stress. And then during the unloading, we have a little bit swelling. So the volume will increase a little bit with a much smaller slope here. So we can see that V naught is coming from the consolidation line and the unloading line to the current specific volume. And for the failure point, we have the starting point at this point A here, and then we start triangle compression. The triangle compression gives us this total stress path. And because it's undrained, we have to utilize this condition here. The final, the failure specific volume and the initial specific volume, they are the same. Then we find the failure point on the critical state line. Then we project back to the critical state line on the PQ space. And then we get the possible effective stress path on this PQ space. Then we find the failure point. The one thing I want to mention here is that even though the effective stress path, it seems to cross this critical state line and then come back, but in the three-dimensional space, everything is happening under the critical state line and before they reach the critical state line to reach the failure. So this crossing is not a real crossing, it's crossing underneath the critical state line. Then we can find the failure deviated stress, and then we find the undrained shear strength. To look at the failure specific volume, and this point is at the critical state line. So we follow the critical state line to find the failure mean effective stress.
我是他妈的，这什么鸡巴东西呀！我操！我他妈人看傻了，他妈这1个小时学的。Wise men say only fool 什么什么 in love。 我记得我好像在哪看，有一个很屌的人，就是很装逼嘛，就是拿手指就这么硬搓火柴，那个搓着了，再扔掉。我操！呼，very nice.
So what about the over-consolidated clay under the undrained shear test? What is the undrained shear strength? This one is a little bit more complex than the
It's too much complex initial state of the consolidated. Consolidated normal condition at Pmax. And then allow the swell to swell the line. V fail 等于 V 0，你 V fail 怎么会等于 V 0呢？Max. Care. 什么鸡巴东西？我操！
So what about the over-consolidated clay under the undrained shear test? What is the undrained shear strength? This one is a little bit more complex than the normally consolidated clay. In this one here, firstly we need to consolidate the solid under the isotopic normal consolidation line to reach the Pmax. And then we unload the solid to the current stress state. If it's isotopically consolidated, the unloading is still on this horizontal axis with zero deviated stress. And on this deviated space, we have the normal consolidation line and unloading line. And on this semi-logarithmic scale, we have a straight line coming down and a straight line going back. And the slope on the normal consolidation line is lambda, and the unloading line is kappa. It's similar to the sigma v and v space when we draw the normal consolidation line and unloading reloading line. But in here we use the logarithm p over the specific volume v. When we look at the initial, this is the initial state, and we have the initial volume. The initial volume will going through this normal consolidation line here, which is from here to the maximum mean effective stress. And then during the unloading, we have a little bit swelling. So the volume will increase a little bit with a much smaller slope here. So we can see that V naught is coming from the consolidation line and the unloading line to the current specific volume. And for the failure point, we have the starting point at this point A here, and then we start triaxial compression. The triaxial compression gives us this total stress path. And because it's undrained, we have to utilize this condition here. The final, the failure specific volume and the initial specific volume, they are the same. Then we find the failure point on the critical state line. Then we project back to the critical state line on the PQ space. And then we get the possible effective stress path on this PQ space. Then we find the failure point. The one thing I want to mention here is that even though the effective stress path is seen to cross this critical state line and then come back, but in the three-dimensional space, is everything is happening under the critical state line and before they reach the critical state line to reach failure. So this crossing is not a real crossing, it's crossing underneath the critical state line. Then we can find the failure elevator stress, and then we find the iron shear strain. To look at the failure specific volume, and this point is at the critical state line. So we follow the critical state line to find the failure. We follow the similar procedure like what we did for the normally consolidated clay and find the undrained shear strain. So we start with the initial volume and the failure volume are the same, and then we substitute the failure volume is on the critical state line, this one here, and the initial volume is coming from the normal consolidation line and unloading line, which is this one here. And then we can try to find the PF. After we find PF, we can find QF, and then we can find SU. However, the whole process is a little bit more complex than the normal consolidation line. What we find at end, we can get a formula like this. So it's still SU over the P naught for barcode over consolidated line is related to M, and it's related to lambda kappa, and also is related to the over consolidation ratio, which is the maximum P prime and then over the P naught prime. So we can see here in this formula, we introduce a new parameter here, R. And R is defined as the P max over P critical state. So this ratio is on this logarithm P space. So what do we see here? We can find the P max with the maximum consolidation stress, and the P critical state is this point here, is the unloading line crossing with the critical state line. But this crossing is the projection. So this, when this line is under unloading, it did not intersect with the critical state line, but on the projected, on this space, these two lines are crossing each other. So this projected crossing, we call it the P critical state prime. And the ratio between the P max and the P critical state is R. And the R can be calculated using this formula here. So it's a P max over P critical state, and it's an exponential function of n take away gamma and lambda take away kappa. The derivation or the steps to get this formula from this point, starting point, can be found in the lecture notes in the reading materials. They give you the detailed derivation steps. We follow the similar procedure like what we did for the normally consolidated clay and find the undrained shear stream. So we start with the initial volume and the failure volume are the same, and then we substitute the failure volume is on the critical state line, this one here, and the initial volume is coming from the normal consolidation line and unloading line, which is this one here. And then we can try to find the PF. After we find PF, we can find QF, and then we can find SU. However, the whole process is a little bit more complex than the normal consolidation line. What we find at end, we can get a formula like this. So it's still SU over the P naught for the over consolidated clay is related to M and it's related to lambda kappa, and also is related to the over consolidation ratio, which is the maximum P prime and then over the P naught prime. So we can see here in this formula, we introduce a new parameter here, R. And R is defined as the P max over P critical state. So this ratio is on this logarithm P V space. So what do we see here? We can find the P max with the maximum consolidation stress. And the P critical state at this point here is the unloading line crossing with the critical state line. But this crossing is the projection. So this, when this line is under unloading, it did not intersect with the critical state line, but on the projected, on this space, these two lines are crossing each other. So this projected crossing we call the P critical state prime. And the ratio between the P max and the P critical state is R. And the R can be calculated using this formula here. So it's a P max over P critical state, and it's an exponential function of N take away gamma and lambda take away kappa. The derivation or the steps to get this formula from this point, starting point, can be found in the lecture notes in the reading materials. They give you the detailed derivation steps. So we have been talking about all the shear strength and undrained conditions of clays. Now let's look at the drained shear strength. We have talked about this before. We said under the drained condition, the effective stress mass and the total stress mass, they are always the same. And to find the failure from the starting point, and we only need to know the total stress mass, and that is the effective stress mass, and when I reach the failure on the PQ space, then we can project this down to the critical state line on the PV space, and to have the starting point and the end point. For a loose sample, we have a volume contraction, and for the dense sample, we have the volume increase dilation. And the characteristics is that because it's a drain test and the water is allowed to drain out during the shearing, and they will generate a volume change and it will generate a volumetric strain. So we have been talking about all the shear strength and undrained conditions of clays. Now let's look at the drained shear strength. We have talked about this before. We said under the drained condition, the effective stress mass and the total stress mass, they are always the same. And to find the failure from the starting point, and we only need to know the total stress mass, and that is the effective stress mass and the rate of failure on the PQ state. Then we can project this down to the critical state line on the PV state, and to have the starting point and the end point. For a loose sample, we have a volume contraction, and for the dense sample, we have the volume increase dilation. And the characteristics is that because it's a drain test and the water is allowed to drain out during the shearing, and they will generate a volume change and will generate a volume measure strain. So when we look at the clay strength, we look at undrained shear strength of over-consolidated clay versus the non-consolidated clay. We said they're all related to the initial mean effective stress, and for the over-consolidated clay, the over-consolidation ratio has been involved in calculating the undrained shear strength of the over-consolidated clay. And all the other parameters, the lambda, kappa, they are always needed when we calculate the undrained shear strength, because that's the characteristics of the solid itself. When we start to look at the undrained shear strength for over-consolidated clay, we said that when the OCI equals to 1, that becomes a normal consolidated clay. So we can use this formula, using the OCI equals to 1, we get the normally consolidated clay, the strength formula. And we previously have this one here, so we can either use this or this to calculate the undrained shear strength. That should be the same value, because we know that R is a function of all the soil parameters here. If we use this one as non-consolidated, this one as over-consolidated, we can look at the ratio of SU for over-consolidated soil and SU for non-consolidated soil. When you put the ratio here, at the end,
哇靠，这是个什么鸡巴东西呀！
and the R and R tensor is only related to the over-consolidation ratio, which means the over-consolidated clay undrained shear strength can be calculated by the normally consolidated clay, the undrained shear strength times the over-consolidation ratio in the power of this value here. This is an example question to look at the undrained shear strength change with the over-consolidation ratio. We give you the range of the slope of the critical straight line on the PQ space. So normally the M is between 1 and 1.5, and the normal consolidation line or the critical straight line slope can be related to the slope of the unloading line. So it's larger than, lambda is always larger than kappa, but in the range between 5 kappa and 10 kappa, so it's not too large and not over 10 times kappa. And if we know n, gamma, and lambda here, and we give you the n is 1 and lambda is 5 kappa, we can calculate this ratio here, which is 0.8. We can also calculate the R. When we substitute all the solid parameters here is approximately 2. So those are the parameters we need when we calculate the untreated shear strength for overly consolidated clay. These are the formulas we can use. For normally consolidated clay, we can calculate the ratio of SU over the P naught, and we get the ratio is 0.282. And from this one, we can calculate any soil and over consolidated status.
Come here.
The normally consolidated strength ratio times the over consolidation ratio in the power of this ratio here. But the one thing I want to mention here is that we can use a different formula to use the over consolidated clay formula, but assign the OCR to 1. When we use this formula, we get a ratio is 0.287, which is just slightly different from this ratio we calculated. I want you to think about this to tell me that why these two are slightly different. Are they both good formulas? Should they both give you the exact solution? Okay, so these are the calculation results. When we say all the soils and the mean effective stress is 100 kPa, what we mean here is that soil is embedded at the same depth underground, and the current mean effective stress, they are the same. However, when we have the same soil embedded in the same location, but if the path maximum mean effective stress that experienced are different, and the over consolidation ratio can be different, even the initial stress are all the same. If the soil is normally consolidated, the untreated shear strength is about 28 kPa. If it is very heavily overly consolidated, which means that it experiences a very high stress level in the history, and the current stress is 100 kPa, and the untreated shear strength can increase dramatically. So we can see that the OCR, the over consolidated ratio, or the past maximum experienced stress, can have a very large effect on the untreated shear strength of the soil. So we see that for a given soil at a given depth, which means the P naught are the same, the untreated shear strength depends on the current value of P naught and on the past maximum value of the stress, which is the OCR. So OCR has...
哎呦，我的亲哥，你在讲的什么呀？我他妈一点也听不懂，他妈是，我操！我搞了1个半小时，我就没听懂几句话，我操！妈的，他妈难顶顶！妈的，我眼睛他妈怎么又变小了？我操！眼睛有点凸了。哎，算了，小就小吧，无所谓。透他妈！4道题 ，We usually use graded state. Which statement is correct? 总是以曲线 PQ、PB。不对，各项同性条件下不接线，一为不接线临界状态。我刚鸡巴给关了，我操！太阳拳，对，架子，那个，对，不对，看角度是最大的。 more. Isolate on top. 对。Main AOS top immediate. 那还是会推下子。你他妈怎么 bottom 的？不正确 ，no volume change， 对。Total stress path is used to find the failure. Total stress path. Effective stress are always the same. There's no expectation generation. 你肯定错了。Is used to find the failure state. For a dream test, which statement below is correct? And dream test incorrect. Oh, 不对，这题有问题，有问题。我他妈操你妈了！ 我他妈第2题是不是对了？我操！Which one is incorrect? There's no extra professional generated. 他妈不肯定是 C 吗？我靠 ，C 不对。C 对了，那你这么说 there's no excess pressure generated by during the soil stream shearing. No volume change. 你他妈我操！你这不他妈刚说是不对的吗？怎么又对了？我他妈操你妈了！ 你妈了个逼，老子妈不信了，我操！他妈日你奶奶！我靠！我他妈日你妈！你他妈咋他妈变了鸡巴体？我操！他妈难道是 no volume change？他妈的 drain 的，我操了！他妈的狗养吧！我操！他妈这鸡巴赶着 drain 的。妈了个逼滚
This is the last lecture of this semester for this unit.
Lovely.
Learned solid strength, like the undrained shear strength of soil, the drained strength of soil, and can use the critical straight line on the PQ space and on the PV space to find the solid strength when the stress parts reach the critical straight line. Today, we're going to look at soil strength profile. This means the soil strength changes with the soil depth.
Say it again.
The critical straight line. Today, we're going to look at soil strength profile. This means the soil strength changes with the soil depth. Let's look at this 1B consolidation case. In here, we want to look at the ratio of undrained shear strength over the mean effective strength or undrained shear strength over the effective vertical stress that the soil is having at the moment. And we look at the normally consolidated clay under the 1B consolidation conditions. So these are the critical straight line, normal consolidation line under the 1B, normal consolidation line and isotropic conditions. By looking at the strength of the soil, firstly, let's look at the vertical effective stress profile. I'm sure all of you can draw this sigma V prime with against the solid depth. So if the gamma saturated is 18 kilonewtons per cubic meter and gamma water we use 10 kilonewtons per cubic meter, and then the effective unit weight becomes 8 kilonewtons per cubic meter times Z, which is linearly increasing with depth. So then we can calculate at 10 meters depth, we have 80 kilopascal of vertical effective stress. From the vertical effective stress, we can draw the profile of the untrained shear strength. We say the untrained shear strength is about 0.2 times the vertical effective stress. So if we do that, we have the at 10 meters depth, the untrained shear strength of soil is 16 kilopascal. And along the depth of this soil layer, the gradient of the strength increasing with depth is 1.6 kilopascal per meter. So how did this 0.2 sigma V prime, where is it coming from? Let's look at this 1B consolidation case. In here, we want to look at the ratio of untrained shear strength over the mean effective strength, or untrained shear strength over the effective vertical stress that the soil is having at the moment. And we look at the non-consolidated clay under the 1D consolidation conditions. So these are the critical state line, normal consolidation line, and the 1D, normal consolidation line, and the isotropic conditions. Now looking at the strength of soil, firstly, let's look at the vertical effective stress profile. I'm sure all of you can draw this sigma V prime with against the soil depth. So if the gamma saturated is 18 kilonewton per cubic meter and gamma water is 10 kilonewton per cubic meter, and then the effective unit weight becomes 8 kilonewton per cubic meter times Z, which is linearly increasing with depth. So then we calculate at 10 meters depth, we have 80 kilopascal of vertical effective stress. From the vertical effective stress, we can draw the profile of the untrained shear strength. We say the untrained shear strength is about 0.2 times the vertical effective stress. So if we do that, we have the at 10 meters depth, the untrained shear strength of soil is 16 kilopascal. And along the depth of this soil layer, the gradient of the strength increasing with depth is 1.6 kilopascal per meter. So how does this absolutely calculate at 10 to 5? I'm sure all of you can draw this sigma V prime with against the soil depth. So if the gamma saturated is 18 kilonewton per cubic meter and gamma water is 10 kilonewton per cubic meter, and then the effective unit weight becomes 8 kilonewton per cubic meter times Z, which is linearly increasing with depth. So then we calculate at 10 meters depth, we have 80 kilopascal of vertical effective stress. From the vertical effective stress, we can draw the profile of the untrained shear strength. We say the untrained shear strength is about 0.2 times the vertical effective stress. So if we do that, we have the at 10 meters depth, the untrained shear strength of soil is 16 kilopascal. And along the depth of this soil layer, the gradient of the strength increasing with depth is 1.6 kilopascal per meter. So how does this remember from the last exercise questions, the example question, we got this ratio here. We said for normally consolidated clay, the ratio of SU over the mean effective stress is 0.282. Again, if we know how to calculate the mean effective stress, and we know the K0, which is the ratio of horizontal stress over the vertical stress, and we can calculate the horizontal stress based on the vertical stress. Then the mean effective stress becomes the sigma V plus 2 times of sigma H, because in the horizontal directions we have 2 directions in the strain in 3-dimensional space. By using this one, by using K0 equals to 0.6, which is a very common value as well, we have the mean effective stress is 2.2 times of the sigma V prime divided by 3, and we have the ratio of 0.733. If we substitute this one into this formula here, so we change this P prime to the sigma V prime, and then we have the ratio of untreated shear stress over the vertical effective stress, and the ratio should be the 0.282 times the 0.733, and that's 0.2. So that means for normally consolidated clay, the untreated shear strength is about 0.2 times of the vertical effective stress. And this we use quite often as an estimation when we look at the soil underneath the ocean under the seabed. If we know it's normally consolidated, if we know the effective unit weight, we can estimate what is the untreated shear strength profile look like. For the soil strength profile of a normally consolidated soil, what we can see here is that the soil strength at the surface is 0, and this is not very good because a 0 strength cannot support anything or any foundation above it. To improve the situation, we can add an extra layer of soil or 6 inches of sand to generate extra vertical stress. Then we allow the soil underneath to consolidate, because we know that when we add a stress on top of the surface here, the extra loading will add on the water pressure first, and then to generate the excess water pressure, when we let the excess water pressure dissipate and the consolidation to happen, then gradually this loading will be added on to the soil particles to increase the effective stress. So after the consolidation completed, the effective stress will be increased by 100 kPa from top to bottom of this soil layer. When we increase, after we increase the vertical effective stress and the soil strength, and the shear strength can be increased by using the 0.2 sigma V prime. So we can see this is one way to improve the soil strength profile underneath the surface. So these are the improved vertical effective stress. To improve the situation, we can add an extra layer of soil or 6 inches of sand to generate extra vertical stress, then we allow the soil underneath to consolidate. Because we know that when we add a stress on top of the surface here, the extra loading will add on the pole pressure first, and then to generate the excess pole pressure. When we let the excess pole pressure dissipate and the consolidation to happen, then gradually this loading will be added on to the soil particles to increase the effective stress. So after the consolidation completed, the effective stress will be increased by 100 kPa from top to bottom of this soil layer. When after we increase the vertical effective stress and the soil strength, and the shear strength can be increased by using the 0.2 sigma V prime. So we can see this is one way to improve the soil strength profile and the surface.
怎么就等于20了？
So these are the improved vertical effective stress and improved the shear strength. There are other ways we can improve the situation of the low shear stress at the surface. So the first one we talk about is to spread some sand layer on top. And the second one is to evaporate water. So the evaporation of the water from the surface, we will reduce the water table. And for any soil, like clay type soil, if we reduce the water table and the soil above the water table normally is saturated with capillarized water, and the capillarized water will give you negative forward pressure, and that will increase the effective stress above the water table, and that can increase the soil strength. And if the evaporation is higher, and they can make the soil above the water table is dry, and we know that when clay is dry, it can have a very high strength. The other one is to say, by reduce the water table using a pump. So we can have a pumping well, and then we pump water out of the soil layer to reduce the water table to a lower level. So in this way, we can have the capillarized water in the clay as well above the water table, and to have a negative water pressure to increase the vertical effective stress. Now we know how to calculate the strength profile for normally consolidated clay. In here, we look at the strength profile for over-consolidated soil. To start the soil, starting with the normally consolidated clay, and we can use this formula to calculate the shear strength. So from this is the effective vertical stress, and by using this vertical effective stress, we can calculate SE, which is this one here. So this is the normally consolidated soil with the shear strength increasing with depth. For an over-consolidated clay, it has to experience a higher stress in the history. So we say this is the stress in the history when there's an extra fill layer on top of it. So after consolidation, and the effective stress is increased due to the surface loading. And due to the increase of vertical effective stress, and we can calculate the increase and shear strength. For the soil to be over-consolidated and the extra stress applied on top of it needs to be removed. So after the extra stress removed from the top of the solid surface, and the vertically affected stress is come back to its original value. However, the untrained shear strength is not coming back to its original value here. The untrained shear strength is reduced a little bit from the peak stress level, but not coming back to its non-consolidated state. So this soil strength profile is the untrained shear strength for over consolidated clay, even though when the vertically affected stress comes back to its original location.
什么鸡巴意思？我操！
So where is the soil strength profile for the over consolidated clay coming from? This table shows you the working process for that soil strength profile for over consolidated clay. The first column is the soil depth. We try to avoid the 0 point because it will give you a zero stress and it will give you infinitely large OCR when we look at the OCR later on. So we pick up a point very close to the surface, but below the surface, 0.1 meters, until the depth of 50 meters and ground. Then we can calculate the vertical effective stress by using the 8Z. 8 kilopascal per cubic meter is the effective unit weight, and Z is the soil depth. By using the 8Z, we can calculate the soil vertical effective stress against depth, which is 0.8 kilopascal. I'm using the kilopascal here, which means all the values I reported here is has a unit in kilopascal. So it's 0.8 kilopascal at surface and 400 kilopascal at 50 meters. After we calculate the vertical effective stress, we can use this one to calculate the untrained shear strength for non-consolidated clay. So just all the values on the second column times 0.2, we get the untrained shear strength of soil at a different depth. So 0.16 kilopascal near the surface and 80 kilopascal at 50 meters. After we allow the surface loading of 100 kilopascal at the surface, then we have the maximum effective stress increased by 100 kilopascal. So this increase is due to the loading at the surface, and also when the consolidation process finishes, when all the excess port pressure dissipated. So this for a 50-meter clay can take a very long time. But anyway, with the surface loading in the history of the soil layer, and after the total consolidation, the 100 kilopascal is the add-on the effective stress at a different depth. So for the surface, the point close to the surface, they change from 0.8 kilopascal to 108 kilopascal. At 50 meters, from 400 kilopascal to 500 kilopascal. For the soil to become over-consolidated, at least 100 kilopascal loading has to be removed. After the removal of this 100 kilopascal of vertical loading, the vertical effective stress will come back to its original value. And because this is the maximum vertical effective stress experienced by the soil, and this is the current vertical effective stress of the soil at different depth, then we can calculate the over-consolidation ratio by looking at the maximum stress and the current stress. So that's why we said that we want to avoid solid depth 0. When this becomes 0, and the ratio OCR can be infinitely large. When we calculate the OCR at different depth of the soil, we can see that the OCR can be 126 at the point near the surface. But when you go deeper and deeper into the ground, the OCR can be just a little bit over 1 at 50 meters, which means this 100 kilopascal loading in the history above the soil surface has a very large effect near the surface, but the effect is getting less and less when the soil depth is going deeper. Then we can use this OCR and use the undrained shear strength of normally consolidated clay to calculate the undrained shear strength of this over consolidated clay with a different of.
哎，我操你妈！
The effect is getting less and less when the soil depth is going deeper. Then we can use this OCR and use the undrained shear strength of normally consolidated clay to calculate the undrained shear strength of this over consolidated clay with a different OCR. If we look at the ratio between the undrained shear strength of over consolidated clay and the undrained shear strength for normally consolidated clay, because the P naught for both clays are the same, is all these values here, then we can use the OCR to calculate the over consolidated clay and its undrained shear strength. By using the OCR, using the parameters we know, then we can, this value is coming from the last example question, and then we can calculate the undrained shear strength along the soil depth for overlay consolidated clay. So you can see here, is a very large increase of the undrained shear strength near the surface from 0.16 to 7.7, from 0.8 to 10.8. When you go deeper into the soil at 50 meters, the initial undrained shear strength is about 80 kilopascal, and after the loading and removal, and the undrained shear strength increased to 95.6 kilopascal. So the influence of this over-consolidation by extra layer of soil acting on top of the soil layer will have a dramatic influence for the soil near the surface and has less influence to the soil deep. Now we can look at the soil strengths under the drained and undrained conditions for normally consolidated clay and over consolidated clay. So if we have a normal consolidated clay, the soil will be consolidated along this normal consolidation line. And if it's isotropic consolidation, and the soil sample will be consolidated to the current state along the horizontal axis. Under the drained condition, we know that for triaxial compression, this is a total stress line, and it is also the effective stress line. So when this line reaches the critical state line, we find the failure point. And the failure point from the PQ space can be projected back to the PV space. So after PV space, we can find that the body is decreased. So the soil is under contraction. If we look at the undrained test, for the same soil sample, we do an undrained test, no volume change. And this is how we find the undrained shear strength. And we project this failure point back to the critical state line and the PQ space and find the possible effective stress path on the PQ space. So under the triaxial compression test, this for the undrained test, this becomes the total stress path. This is the effective stress path, and the difference at failure, the difference between the total mean stress and effective mean stress, and giving the positive pole actually generating and sharing. What about the over consolidated clay? So if we have a clay that experiences a very high stress and then reduce to the current state, and we can find this point to say it is under isotropic consolidation and isotropic release of the stress, and this is current stress that soil is experiencing.
我大声。
Then we can start at a drained test. Under the drained test, the effective stress path and the total stress path, they are exactly the same. Then we have this on the PQ space, this stress path reach the critical state line to find the failure point, and we can project this failure point back to the critical state line on the PB space, and we find the volume is increased. If we do an undrained test, we know that no volume change, and we can find the failure point on the PV space, and we project this back to the PQ space, and that's the starting point. This is starting point, this is failure point, and this is the possible effective stress path. So we can see here for a drained test, the strength is depending on the initial effective stress at the starting point, and also it depends on the total stress path and effective stress path, they are the same. So when you know the stress path, you know the initial stress point, you can find the strength of the soil when I reach the critical state. When we do an undrained test, for this soil A and soil B, because the initial water ratio on the state, for one is over consolidated, one is non consolidated, and they will give you exactly the same undrained shear strength. So we say the undrained shear strength is depending on sometimes only on the initial water ratio, or it depends on the initial mean effective stress and the OCR. For these two soils here, the soil A has a very low initial mean effective stress, but it's over consolidated, the high over consolidated ratio.
妈，直接是不是写邮件啊？可以。Professor.
So how does the construction loading change the soil stream profile underneath? For example, if we have a tank or gravity-based structure built on top of the soil surface, and the soil initial undrained shear stream is increasing linearly with depth, and surface can have a little bit of strength or have a zero strength. For soil have a little bit of strength, it shows that the non-consolidated clay with the surface layer being taken away and transported to another location, then the soil surface may have a little bit of strength. But the gradient will be the K, and the K is in the range of 1 to 2 kPa per meter. The example we show you is 1.6 kilopascal per meter. So for the undrained shear strength, this non-consolidated clay to certain stress level, and the undrained shear strength can be defined from the PV space and projected back to the PT space, and this is undrained shear strength. With the loading added on top of that, initially this undrained shear strength is effective, but gradually with the surface loading adding on to the soil particles, when the excess port pressure dissipated, when the consolidation is gradually happening, so the surface loading will be gradually transferred to the soil particles. With the complete consolidation process, with all the excess port pressure dissipated, the effective stress is increased by the amount of the surface loading. So with the increase of effective stress, this is normal consolidation line. So the mean effective stress is increased from the initial condition. At this particular location, at this stress condition, the undrained shear strength can be found on the PV space and projected back to the PT space. You can see here, when the consolidation process is completed, the undrained shear strength of soil is improved from this value here to this value here after consolidation. And we also know that with this loading, the SU value can be increased dramatically at the soil surface, but the increase is gradually reduced when it goes deeper underneath the surface. And the soil strength at the center of this gravity-based structure, it becomes more or less uniform after the consolidation. We're talking about the consolidation to say when it's totally finished, totally completed, but for a big layer of clay, this consolidation process can take a little while, a long time. And the stability of the structure increases with time because the consolidation process, because the effective stress gradually increases with time. So when the undrained shear strength is relatively low to start with, we certainly don't want to add enough loading to fail soil, because once the soil reaches the critical point, it will fail. If the loading is going to fail the soil straight away, we can do a stage loading to improve the soil strength before we add the total load on top of the soil. So what is the stage loading? How do we improve the soil strength? So if we have a soil is isotropically consolidated to this stage, and then we start the construction, we can load it undrained, because for clay the permeability is so low, when you add loading on top of it, the initial stage is always undrained. Before we reach the failure, we stop. So we add a little bit of loading and we now reach the critical state line. Then we can project this back to the PQ state. Now we stop. When we stop, the consolidation process will start. Because the loading, the entry loading initially is added on the excess port pressure. So the port pressure will increase by loading. And then when you stop loading, the port pressure will start to dissipate. During the excess port pressure dissipation, and the deviated stress will not change. Because the deviated stress is the difference between the vertical stress and the horizontal stress. When you change the port pressure, the difference between the horizontal stress and vertical stress will not change because the port pressure change in all directions are the same. So the difference will be the same. So this is the consolidation process when the Q is constant. Then we project this point back to the previous phase. Then we load again. The loading is undrained. Before we reach the critical state line, before the failure happens, we stop and we wait. Then we have this consolidation again. So we let the solid consolidate, let excess port pressure to dissipate, and then come to the point 5. We project point 5 to the previous phase. At point 5, we can find a new undrained shear strain. So if we load its undrained condition, this is the point of failure. So if we project this back to the critical state line on the PQ stage, and this is the undrained shear strain after 2-stage load. So you can see here, the undrained shear strain initial soil is this level here. After 2-stage loading, the undrained shear strain is improved to this point here, so it's an increase quite a bit. However, when the soil layer, when the clay layer is relatively thick and the clay permeability is relatively low, this stage loading can take a while to complete, and then the soil strain can be improved. To improve that, before we finish this session, I want to show you a few laboratory test data for traction tests. So on this slide, we show you the cleaned test, and for these 2 different sands. One is the silica sand, and one is the calcareous sand from Ireland, the Dawson sand. For the silica sand, and the minerals is mainly quartz, and for the calcareous sand, the mineral is calcite. So this is the soil test result with the actual strain and deviated stress. And this different test is under different cell pressure. So we can see here under the when the cell pressure is increasing and the deviated stress at the peak and the residue is increased as well. And all the soil samples we tested shows dilation. And under the lower cell pressure, the dilation is higher, and at higher cell pressure, the dilation is lower.
What?
For the calcareous sand, we can see here, this is also the actual strain and deviated stress. And under the low cell pressure, we can see a peak, but under the high cell pressure, and the peak cannot be observed. And if we look at the volumetric change against the actual strain, under the high pressure that we have contraction, and at the low pressure we have a dilation. So we can see here for the calcareous sand or the dog spit sand, we can see that the cell pressure, how they change the dilation and contraction of the soil behavior. And that's because the calcareous sand is more angular and it's more compressible. And the quartz sand is less compressible, and that's why it's easy to dilate in sharing. On this slide, we will show you the traction test results for drained and undrained tests on the dog spit sand, which is the calcareous sand. We already observed the soil behavior on the drained test. We said the soil under higher cell pressure behave like soil, which the volume is contract, and under low pressure, the soil behaves like dense soil, and the soil volume is dilate, because the vertical axis is the volumetric strain. For the undrained test, we draw the effective stress path on the PQ space. So P is the mean effective stress. And this volume graph is showing the actual strain and the excess port pressure generated in sharing. So what we can see here, we can just pick up one sample. Is isotopically consolidated to this stress level, like 600 kilopascal. Under loading, we do a traction compression test. This is the same soil. If we put of this unit, excess port pressure.
真鸡巴的头痛，我操，根本就不知道他在讲啥，头痛。直接做，柜子直接做。对于正常不减人头挺不看。我操！我操 ！Normal consolidated soil。正常估计。Normal consolidated。Undrained。Soil strength 什么0.2倍那个我记得。 effective stress related to the vertical effective stress. Module 5. Lecture 4 quiz. Module 5. Quiz. Module 5. Lecture 4 quiz. For drain and entry space on the clay. To undrained sources. 他妈的玩意，我操！Drains. 啥他妈 TSP 我操！哎，我他妈操你妈！老子根本不会。Undrained shear strength.对了，我操！我就喜欢这种他妈直接就是概念，知道咋做的。你鸡巴弄个他妈屌逼鸡巴抽象概念在那讨论，我他妈咋知道 ？Improve. 哪一个不正确？Consolidation. Dilation stress. 啥他妈的玩意呀！我的操！ Under first load. 我操，得个30分，第二题错的。做公路，看这都烦。哎，你滚吧！我操！我尊一下。一进入教室，课还这个写，我操！14号，我操！一会儿又就过7个球。我他妈睡一会儿，他妈起来接着搞这个，真他妈恶心。